The last time, excuse me, the last time, ladies and gentlemen, we took notes. We were discussing thermodynamic equations, dealing with heat, dealing with exothermic, endothermic reactions. We're going to do a lab. I believe that lab will be Monday over exothermic and endothermic reactions. Yep. You have a pre-lab video tomorrow for homework. Okay. It'll be assigned for you tomorrow, so you'll have to do it over the weekend. We're going to be doing a lab endothermic, exothermic. Today we're going to talk about a little bit more on heat and reactions, and we're going to get into the enthalpy, which is abbreviated H. You might as well take out your thermodynamic data table because we're going to be using that for the enthalpy also. What is enthalpy? The amount of heat that a substance has at a given temperature and pressure. The amount of heat a substance has at a given temperature and pressure. We cannot measure enthalpy. We cannot measure the enthalpy, the amount of heat, directly. However, we can measure the change in enthalpy. So although we cannot measure enthalpy by itself, we can measure the change in enthalpy, and that change of enthalpy occurs whenever heat is released or heat is absorbed in a chemical reaction. Bless you. So whether we have an endothermic, where heat is absorbed, or an exothermic, where heat is released, we can measure the changes that are occurring with the heat. So even though we cannot measure enthalpy, we can measure changes in enthalpy. The heat that is released or absorbed during a chemical reaction is called the heat of the reaction. And this is important. This is important right here. So you might want to put an asterisk by it. Delta H is positive for an endothermic reaction and negative for an exothermic reaction. So the change in enthalpy is positive, you have an endothermic reaction. If the change in enthalpy is negative, you have an exothermic reaction. And these next couple of slides that you're going to see, folks, these next couple of slides, I think you've seen before. Okay? We dealt with this, and we said that in order for this reaction to occur, in order for calcium carbonate to decompose, we have to have 178 kilojoules of energy. That is an endothermic reaction. If you remember, you have this in your notes a little bit earlier, that right in here, we put that plus 178.1 kilojoules. We put it right in there with the reactants. Okay? So when you would calculate the change in enthalpy here, it would give you a positive number. Positive number tells me that, yes, indeed, that is an endothermic reaction. Or, yeah, endothermic reaction. Likewise, here's another one we dealt with. And we had the negative 393.5 kilojoules here in the product side. And we said that that was given off. So when we calculate the change in the enthalpy, it will give us a negative value minus 393.5 kilojoules. You see that negative sign? You say, okay, that is an exothermic reaction. Enthalpy changes occur when a compound is formed from its elements. Okay, we have a simple combination reaction. The enthalpy measurements use free elements at a standard state of 0. So we arbitrarily set all free elements at the standard state as 0. So go ahead and pull out your thermodynamic table. Look on the front side of that. The very top one is aluminum as a solid. Find the column for entropy, or excuse me, check, enthalpy, the delta H. Which column is it? Which column is it? The very first one. Look at that very first column. Look at the enthalpy. The enthalpy from aluminum as a solid is 0. What is the enthalpy of aluminum chloride as a solid? Negative 705.6. Okay. Let's go over. Okay, let's go over. And if you notice, that is not 100% that everything is 0. Look at cesium on the other page. Cesium as a gas, cesium as a liquid, cesium as a solid. Okay, cesium as a solid is set at 0. The other side, the other column, Garrett. Cesium as a solid is set at 0. Cesium as a liquid, 2.09. Cesium as a gas, 76.50. So we do not always have it arbitrarily set to 0, but most free elements are set at 0. If we are dealing with entropy changes, we use the standard heat of formation, which shows you this little bit right here. If you notice, that is actually what you're reading on your chart, okay? The standard heat of formation. It is the change in entropy for a reaction in which 1 mole of the compound is formed from its elements. The more negative the value of the standard heat of formation, the more stable the compounds. And in order to calculate your change in enthalpy, we simply take the standard heat of formation of the products minus the standard heat of formation of the reactants. So once again, the standard heat of formation of products minus the standard heat of formation of reactants equals the enthalpy. What does that look like? What does that equation look like? The entropy equation, right? Where we have products minus reactants. So do you think this is going to be somewhat similar to what we have been doing with entropy? Absolutely. What's going to be the difference? Yeah, what column we look at on our table. What column we look at on our table is going to be our only difference with this. So, let's check one out here. Let's check one out here. And although I have these, I'm going to do these. I have them already on the slide. I'm just going to do it by hand because I like doing it better like that. So, delta H is going to equal what? Delta HOF of products minus delta HO sub F of the reactants. Correct? Equation we just got. Now, what is my product in this equation? Carbon dioxide. What state is my carbon dioxide in? It is in a gaseous state, correct? So, as I look for carbon dioxide in a gaseous state, I find my enthalpy to be negative 393.5, correct? How many carbon dioxides in the gaseous state do I have? 2 of them. So what do I need to do? I have to have a parentheses and I put a 2 in front of it, right? Now I subtract, and I'm going to put that in black, and I'm going to do my reactants here in blue. just to show that it's a different one. So I subtract my reactants. Now, I have two different reactants. So what I'm going to do is I'm going to put this in big brackets as so, just to signify that I have to have all of this added together before I could subtract it. So I look up my enthalpy for carbon monoxide as a gas, and that is what? What's my enthalpy of carbon monoxide as a gas? Negative 110.5. How many of those do we have? Two of them. So I'm going to put that in the parentheses, multiply it by 2. To that, I am going to add the enthalpy of oxygen. I go to my second page, I believe it is. The enthalpy of oxygen as a gas is 0. So now I've got my values. All I'm doing is just doing my math. Negative 393.5 times 2 is negative, this is a red color, negative 787. From that, I'm going to subtract and my blue value is going to be negative 221. So what I'm going to be doing is I'm going to be taking negative 787 and subtracting negative 221, and I come up with a value of negative 566. What is my label? Kilojoules per mole. Correct? And since that value is a negative value, what does that tell you? It is an exothermic reaction, so heat will be given off, released. So what is the difference? I mean, this is it right here. This is enthalpy. What is the difference between enthalpy and entropy? Okay. What's the difference? Well, number one, we're dealing with two different things. We're talking about heat and disorder. But when we do the calculations, what are the difference in the calculations? The number off of the chart, correct? The number off of the chart. What do you think? Is whether it's gaining or losing order in entropy. Okay, entropy is dealing with the disorder. Okay. No. Like disorder, something that is more ordered is, remember, the solid. It's packed together. It's got that crystalline structure. What about a gas? Okay. Gases are all over the place, bounces off everything, right? That's more disorder. That's what entropy is giving you. This is giving you heat. Whether heat is taken in, heat is released. Okay? Now what we are going to do, folks,